Hi everyone, my name is Juan Chacon. I will be presenting some background and top scoring solutions on the prostate cancer grade assessment Kaggle competition. I want to start by telling you a little about me. I am attending to this meetup since November 2020. I recently got my master's degree in applied math from Simon Fraser University, and I also have a bachelor in electronic engineering. Before starting my master's, I was working as data scientist doing landmine detection, influencer marketing analytics, and credit risk models. I am actively looking for a data science role in Vancouver. And if you know about one or know someone who might know, I will appreciate the connection. During the presentation, feel free to interrupt to ask questions to provide an insight. It would be interesting to know about your thoughts. Before starting, I want to tell you that I brew my own kombucha, and if you want some SCOI, I can share with you. We will start by a brief overview about the competition. Then I will present a baseline solution that I was able to run and will describe some top scoring solutions. I also will comment on a discussion regarding to the instability of the score metric between the public and private evaluation sets. And I will finish this presentation with some very short conclusions. How is my audio? Is it working well? Good.
That sounds good.
Thank you. My last comment before diving into details is that some ideas are a little intricate, but I will try my best to simplify them. Let's get started with the challenge review. This competition was launched on April 21, 2020 and closed on July 2022. July 22, yeah. So the prices for this competition sum up to $20,000, and this was a code competition. And some of the requirements were that the CPU time should not exceed 9 hours, while the GPU runtime should be less than 6 hours. Neither TPUs nor internet access will be available, but external data will be allowed. These include pre-trained models. First, I will start by mentioning why this is a relevant problem. Prostate cancer is the second most common cancer among males worldwide, and it results in more than 350,000 deaths annually. And the key to decrease mortality is developing more precise diagnoses. In the figure on the left, the diagnosis of this type of cancer is based on prostate tissue biopsies. They are examined by a pathologist who scored them based on a Gleason grading scale. In the figure on the left, we can see some Gleason patterns. The grading scale is defined according to the glands, those white cavities in the tissue. Less cavities imply a higher score. Depending on the two majority Gleason patterns in the tissue, experts formulate the ISUP grade, which measures the risk of prostate cancer, ranging from 0, which means no risk, to 5, meaning high risk of cancer. For example, in this figure, most of the unhealthy tissue was a Gleason pattern 3, and it has a Gleason pattern 3. This is called the majority, while the second most common, the minority, has a pattern of 4. These two combined form a Gleason score of 3 plus 4, or equivalently an ISUP grade of 2, which means a moderate risk. The task for this competition is to predict the ISUP grade from whole sliding images biopsies. Each of the biopsies is stored in a TIF file with 3 different resolutions, allowing up to 16 times more resolution on higher quality images. Many competitors used intermediate resolution in their solutions. Let's go with the data description.
Yeah, I got a question on that one too. Go for it, David.
Yeah, I was just going to ask a random question.
In the previous one?
So, like I was wondering if you knew anything about the dye they use for the biopsies, what it's specifically like bonded to.
Sorry, could you?
It looks like all of the biopsies have used some sort of a dye in order to color the tissues to highlight some of the features in them.
I don't quite get the question. So.
Oh, it's fine then. It's not a data science question. It's just about the underlying stuff.
How they are sampling, but so sorry. Could you repeat it? Maybe I can get it.
I was just wondering if you knew anything about what dye they used to color the tissue biopsies.
No, I have no idea.
I mean, that's fine.
Okay.
Juan, I have a question also on this page. I'm trying to understand what a healthy tissue and what an unhealthy tissue would really look like, to try to understand kind of like the problem that the machine learning is trying to solve. So on the bottom left, you have the GS3, that would be the healthiest, and then the 4 and the 5, and that's getting more and more unhealthy.
Yes.
And what sort of features are in 4 and 5 different than 3 that make it unhealthy? Sorry if I missed it, if you already said that.
Yeah, no, I already explained it, but that I think it is good to clarify. There are some regions in the healthy tissue that are white regions that are called glands. Those are kind of some holes that you can see, the white holes that you see there. So a healthy tissue, or one with a Gleason score close to 0, will be more regular and will present or exhibit more glands. For example, in 4 or 5, you don't see those kind of holes regularly, but you see that the tissue is kind of pretty solid, and there are not presence of any holes.
Okay, and there's 2 different images that are taken that are added together. Are those different regions like pre-specified, and they always take certain regions together, or do they? No?
Those are not predefined. I think that you study the biopsy, and you determine what is the pattern, the majority pattern. So what is the pattern that is present in most of the tissue on non-healthy tissue? So you pick the two patterns that are more present in the tissue, and that is what is giving the name for the Gleason score. So 3 plus 4, it means majority 3 and minority 4, or 4-3 will imply the other way around.
Oh, okay. So there's more than just 2 images in the. I'm sure you'll get to it.
Yeah, so. You have to scan through the whole tissue, biopsy tissue.
Okay, thanks.
One more random question here, actually. How many of these tiles do they have per biopsy on average?
So it is supposed that per each patient, they have one slide, but with 3 different resolutions.
But that's just one biopsy, right? But each of those biopsies will have a certain number of these like zoomed in sort of views.
Actually, you have the full files, the full file, and you might scan or split in tiles as you want. So you can scan the figure as you want. So you will have the full image.
So how do researchers do it then? Like it from your description, it sounded like they divide the tissue into sections and then score each section.
I think that they are trained. They are trained. They are trained to analyze what are the sections of the tissue that has more um, possibly unhealthy tissue, and they start analyzing or kind of paying attention more to those areas.
Okay, but you said something about like the majority is the one that gets the first number in the Gleason score, right?
Yes.
So that means that they would have to look at lots of different sections to decide what the majority was, right?
Yes, I would say that they first have to determine what is the unhealthy tissue, and then they need to categorize the categories and define what is the majority and the minority patterns.
Okay.
Okay, great. There is any other question? If not, I will continue. So I was mentioning that we're going to go with a data description. The given data includes biopsy images and some CSV files with some metadata. On the image side, we have 383 gigabytes for more than 10,000 biopsies. With their corresponding mask, this specifying the Gleason pattern segmented by pixel. Different color means different pattern. In the example, green is 4.2 and red is 4.4. The train metadata included an image ID, the data provider, the ISUP, and the Gleason scores. There are two data providers, Karolinska and Radboud. They use similar but different scanner technologies. The final resolutions are different. For the training set, the Karolinska samples are almost half of the data. These samples are graded by a single expert. In contrast, on the Radboud side, each sample is labeled by trained students from previous diagnostic reports. For the testing set, it is not clear how many samples are used. Some competitors estimate that about 400 for the public set and 550 for the private one. The metadata only includes the image ID and the data provided. In terms of test labels, both data providers use three expert consensus grading system. In the Karolinska case, one of these experts was the same who graded the training samples. Let's see some training set histograms. First, from the Gleason score histogram, we can conclude that the Gleason score distribution is not uniform for the training data, and also that the most common Gleason patterns are 3+3 and 0+0, while 3+5 and 5+3 are very rare. In terms of ISUP grade, from the right histogram, we can conclude that most of the data provided by Karolinska, the green ones, have ISUP grade 0 or 1, while the distribution among ISUP grades for Radboud is more uniform. Also, Radboud provides more samples of patients diagnosed with high risk of cancer than Karolinska. Is there any question here, maybe? If not, I will continue.
Quick question.
Oh, sorry.
The 0+0, I didn't see an example of that before. Where does that come from?
I think it was for Radboud. They use 0+0 as convention for unhealthy for healthy tissue.
Okay.
Is that equivalent to negative on that chart?
Yes, it
Okay.
is equivalent. Well, the submissions are scored based on the quadratic weighted kappa, which measures the agreement between two categorical raters. In this case, our classifier versus a random sampler. This metric typically goes from 0 in the case of random agreement to 1 when there is a complete agreement. However, in the event that there is less agreement than expected by chance, this metric might go below 0. All of this might sound a little confusing, and it was for me at the first time. That was the first time that I saw this this metric. But let's check it with an example. Let's consider the normalized confusion matrix for a hypothetical classifier showed in the left table, the table O. Each column represents one out of the three possible classifier outcomes, A, B, and C. This is a completely different example. That it doesn't have any to do with the ISUP grade. On the rows, we have the actual classes, and this 0.2 in red here indicates that 20% of the times our classifier made the mistake of predicting C when it was actually a B. From here, we can also see that the empirical probability of a prediction of B for this classifier is 0.5, the sum of 0.1 plus 0.3 plus 0.3. Or that the empirical probability of getting an instance of type A is 0.3. Which is 0.2 plus 0.1. Now, on the other hand, if we consider a random sampler with the same per class probabilities but independent of the phenomenon of study, we obtain the following joint probability matrix. This is called E for expected. This is obtained by multiplying the prediction and actual per class empirical probabilities. For example, this green 0.25 is the product of 0.5 times 0.5. Finally, let's focus on the Kappa formula. Let's suppose that for simplicity, let's suppose that we have a weight matrix W with zeros in the diagonal and ones elsewhere. In other words, that it is one where we make a mistake in the matrix and zero otherwise. The kappa metric is comparing how similar are these two matrices when making mistakes. I mean, in the red regions. If there are similar, the quotient is 1, and so the kappa score is 0, 1 minus 1. On the other hand, when the sum of the errors in the random case is much larger than the ones made by our classifier, the quotient is closer to 0, and the metric is closer to 1. In this case, the vanilla kappa score, I mean the one with this weight matrix, for our toy example will be 0.365. The actual metric for the competition uses a quadratic weighted matrix. The emphasis for the emphasis in errors that are closer to the diagonal is less. This implies that mixing up closer cases harms less than mixing classes that are separate in the final score. Okay, I think it was enough for preliminaries. I don't know if you have any questions in this part. Okay, I will go then. Let's go with the baseline model. I will present a transformation of the dataset, the model details, and my experience running the baseline. The original dataset is very large, almost 400 gigabytes. This includes several resolutions for the same image and plenty of white space. Here is where the YAFOS tile extraction method enters to the game. This was proposed by one of the competitors and was widely used by the others. I would say this was the facto approach for dealing with the data. This strategy tries to remove the large empty areas that has no information but requires large memory usage. Instead of passing on an entire image as an input, some tiles are selected from each image based on the number of tissue pixels. And here's how it goes. We white by the original image to get an image size divisible by the target tile size. I am padding here with green for this explanation, but just for illustration. Then we split in tiles. We sort the tiles by area of tissue and select the first N with more tissue. In this example, the number of tiles was 12, and as you can see, depending on the tile size or the size of the image, we will cover more or less tissue area. Using this technique, we are able to reduce the database size from 383 gigabytes to 3.1 gigabytes. I don't know if you have any questions about the tile extraction method.
I have a quick question, sorry.
Yeah.
So how do you come to the ideal number of tiles? I'm thinking like as the number of tiles increase, the more complete of a picture you get, right?
Yeah, that's true, and that's a hyperparameter.
Hello. I have a question too. How do you choose the tile size? Is it different for every slide, or is it the same for all of the samples?
It should be the same.
Hello. Cool. Thanks.
Yeah, that will be the same along all the biopsies. And actually, different solutions try with different tile size, and they get different results. Okay.
Hello.
So,
yep.
So just to confirm where we are, so we started with one image, and now we're at, for each biopsy, now we have n images that are much smaller.
Yeah, exactly like this.
Okay, so then that's going to be the point that we're starting now for the next bit.
Yeah. And those images contains tissue, or that's what we expect, and we try to remove the white space. The ones in, yeah. So great.
I had a question. Hello.
Yeah.
Oh yeah. Hi.
Hi.
This you said we sort these tiles based on how much of their area is occupied by the organ tissue. Is it so it means the relational position of tiles compared to each other, it doesn't matter, because when we sort them, their order is different than original order.
Yes, that's true, and there is a consideration for that in the model. So when we start working with the tiles, we will deal with that spatial relation. So we need to minimize the impact for working with with tiles in this way. But what you mentioned is correct. So we are somehow missing the how close or the local properties that a tile has.
Oh, okay. Because, for example, what I thought is that this way, some maybe there is a for maybe two unusual patterns are in two tiles beside each other. But maybe this doesn't happen in another picture. But when we sort this tile in each picture, we mess with that pattern that was in the data.
Yeah, you're missing that information. But when we were working with the model, or when we study a model, I will tell you where this property is kind of taken into account. I can pause on there and we can discuss, I think.
Oh, so you have taken this into account later, or no?
Yes. Well, my experience here was running the model, so I was not the one that took that into consideration. But yeah, so it was considered.
Oh. And last question: why we need to sort the tiles? Can we come up with an idea to just pack them together without losing their order compared to each other?
Well, the idea of ordering them is try to pick the n. Let's say we want to restrict the number of tiles to n, a fixed number of tiles, and we will select the tiles with more tissue and not the other one. So, for example, the tiles that are completely white, they will be at the end of or of the order. So we are going to exclude them. It's just a way to exclude them. Sorting is just a way to exclude tiles that doesn't include any tissue.
Oh, so there wasn't other way to exclude the white cells without ordering cells?
Yes, sure. I think that for sure there are other ways, but at least this method seems to be pretty effective.
Okay, thanks.
Okay, thank you. Well, I will continue. As you might know, ResNet popularized skip connections, which address the exploding and vanishing gradient problem, allowing to have deeper networks without compromising model generalization power. I won't go over the ResNet details, but I just want to show you a variant of the ResNet model that was introduced in 2017 by Facebook researchers, and it is called ResNext. And it keeps the overall network architecture, but replaces the skip connection convolutional and identity blocks for wider alternatives, introducing a new dimension to grow. That is, this dimension is called the cardinality. Researchers show that increasing cardinality might improve the classification accuracy for some classification tasks. So some tasks. So we will be using this model, removing the final and global pooling layers, and we will use that as a backbone for our baseline. The standard approach to address this problem uses the full image passing through a convolutional model, but as the image has large wide areas, it might take a long time, and it is inefficient as we are passing a lot of white space to a network. Instead of concatenating the tiles at the beginning, the concat type pooling strategy proposed by IAFOS concatenates the tiles after the convolutional part, where there is not much positional information. So in here is where that issue that you mentioned before is addressed. So we will be using the tiles, but we will be concatenating them after the convolution. after the convolution part. Let's see how it is. How is the forward flow for this strategy using the illustration that I have on the right. We start with some tiles of size 128, and then we pass through the ResNext 50 backbone, then a concatenation step followed by a global pooling layer and a fully connected block to get a 6-dimensional output. How did this method modify the forward input processing? Let's suppose that we start with a batch of size 2 biopsies, one biopsy in green and the other one in blue. Then we arrange the obtained tiles in a longer batch as shown. After passing through the convolutional part, we will have reduced spatial dimensions but same batch sizes. The concatenating step along one of the spatial dimensions will reduce the batch size to 2 again. And finally, after passing the pooling and fully connected layers, we will have batch size of 2 corresponding to the predictions for the original biopsies. And this is a smart way to parallelize the computation without growing the architecture. So we are not passing each of the tiles to the model, but instead of that, we are parallelizing them, forming those batches. It was a really clever idea, and I think that these are the kind of things that you can do when you understand pretty well how the tool is working. And I don't know if someone has any comment or question here.
Sorry, yeah, I have a question, but I'm sorry, I got a little bit lost from background sound on my side, so I might be asking you to repeat something here. But so I understand the standard approach, just passing the whole image through a convolutional neural network, and now we're talking about the effective implementation. So we split it up into 12 much smaller images. Do each of those go through a convolution, or are we concatenating the images beside each other and then putting that through a convolution? But by the image you have, it's not that clear.
It is kind of equivalent. So you could do in inference, you could pass each of the tiles through the inference up to, so you can pass them through the convolutional backbone, each of them, and then concatenate them, and then you can concatenate those. That this might be one way to do it, but the other way to do it is put all of them, all of the tiles in the same batch, pass them through a backbone, and then organize them inside of the training loop, and run the head over the concatenated image.
Okay, I'm just trying to understand why you would concatenate them rather than just average them, or yeah, maybe I don't understand.
You have different number of channels at that level. No? After the concatenating, each of the tiles will have like 2048 channels. If you are averaging them in the batch dimension, it won't get the expected effect, because what you want at the end is having like after the pooling layer, you want a vector of 4,000 channels. So after you apply the global pooling strategy, so you will be pulling same channels for different tiles if you concatenate along the spatial dimension.
Okay, maybe we could take a step back. Like, let's just talk about one of those small images. So 3 by 128 by 128. That's going to go through a ResNet, and then the output of that is going to be
Sorry, you are talking about the flow or just one tile?
just one tile.
Okay, yeah.
Okay, and then so what is the kind of end state? Is that's going to be a flat vector, right? That one tile is going to lead to?
After the fully convolutional block, or?
Yeah, so it's essentially going to, is that one tile going to go to a 6 by 1 by 1 matrix?
Yes.
Okay.
If you run it without, so you have to run the concatenating step, but as you only have one tile, you will get only the same input. But when you are running more, you will have like a more long image in the concatenated, or a longer array.
Okay.
And then when you are doing the pooling, you will be doing the pooling over the full concatenated channels.
Mm-hmm.
I had a question here as well. So did anybody check whether this fancy business of putting the tiles in their original place, like their original order, and then rearranging them afterwards to concatenate them, made much of a difference? Because my intuition for this problem is that the cell sizes in these images, like the cells ultimately are the things you want to test, and I think they're relatively small by comparison to like the image sizes. So I would have thought it wouldn't have made much difference whether or not the images were in order. But I mean, I could be wrong about that.
Well, it turns out that the order doesn't matter, and actually the winning solution, the first one, doesn't use this strategy, and the only thing that he did was, or the team did, was organize them in a big square and then run the whole convolutional layer, and it worked. But there is no like a prior fact that makes you think, or at least from my perspective, that using that strategy will work, because you are missing some of the local properties between tiles, and actually sorting into it will be something impossible to do. So there is not an actual order in the tiles now.
Okay, good to know.
Okay. Well, and well, I want to briefly give some details about the training and inference for this baseline model. For training, it uses 12 tiles of size 128, obtained from the lower resolution layer. Do you remember that each of the TIFF files has 3 resolutions? So we are picking the lower one. The ResNext 50 backbone is pre-trained on a semi-supervised task on ImageNet. The training is done using 4-fold cross-validation stratified by ISUP. The used loss is categorical cross-entropy, and it uses some geometric augmentations. The training is for 16 epochs per each fold. For the inference phase, for each of the 4 models obtained in the cross-validation phase, it uses 8-fold geometric test time augmentations. What this means is that for each biopsies, we obtain the prediction, not just for the original image, but also for the other 7 images obtained applying 90-degree rotations and reflections. as shown. This method produced 32 predictions which are aggregated using mean. This baseline model get a public score of 0.79 and a private of 79.4%, which are very similar. So there are any questions about the training or the inference cycles? Well, if not, I will continue. Well, up to here, everything seems to be clear or at least understandable, but there were some limitations. First, and the most important, I had no prior experience with Python and FastAI, and I had only worked with Keras and TensorFlow. And most of the discussions and notebooks in Kaggle were PyTorch based, so I had to start learning fast. Second, my PC has not GPUs, so I had to use the Kaggle ones, but Kaggle has some restrictions, and they are that the GPUs, the quota is limited to 30 hours a week, counting committing, the commit and interactive session runtimes. And second, the disk space is also limited. In the run and save all modes, it's just 5 gigabytes, which is small for generating larger tiles. As this was a code competition, we need to submit a notebook. Instead of writing a unit notebook, I follow the next workflow. First, a notebook for the tile extraction. This one doesn't require GPU. The execution time was about 15 minutes. As output, we produce a 3.13 gigabyte tiles dataset, and we want to create and we have to create a Kaggle dataset. It takes another while, so it is really time consuming. So not just generating, it's just 15 minutes, but then downloading the set or uploading the set in another notebooks takes a while. Then in another notebook, we work in the model training. This requires the GPU, and as it is cross-validated, it takes a while. And it was about 9 hours. We require as input the tiles dataset, and we will get as output 4 datasets. We need to save them as a dataset to import in the final notebook, the submission notebook. For inference, we work in another notebook, importing the cross-validated models and defining the inference pipeline. I have no idea what is the execution time on this notebook, but the full evaluation time for the private and public leaderboards is less than 25 minutes. Up to here, it was my experience running the baseline model, and I don't know if you have any questions. Well, I will continue then. I will present 2 of the top score solutions, the 11th place solution by Yafus and the first one by PANDA team. Before starting with the solutions, I will present 2 short preliminaries and denoising and cutout augmentation. There are 2 possible causes of label noise. First, the labeling is a manual task, so there is chance of human error. And also there are some inconclusive reports that are used for the final diagnostic. And second, as the grading of the training and test were performed by different experts, it could be some expert biases in the labels. So One might expect this issue more evidently in the Radboud dataset, as several students create the training data. An effective strategy to deal with this label noise has two steps: um, label cleaning and assemble of learning or of different learners using the cleaning data. In the label clean step, several models are trained using cross-validation. Then for each sample in the training set, the model that has not seen that particular data point is used to make the prediction. This is called a fold-out prediction. If the difference between this prediction and the ground truth is larger than a given threshold, then the sample is removed from the cleaned train set. This technique removes both the wrong labels and the difficult data, and therefore the model will be weak against difficult data but strong against easy data. I think it is a pretty straightforward technique and will help a lot, at least in terms of the positions. Well, our regularization technique is a strategy to reduce overfitting, or the same as increase generalization power of a model. Some examples are decaying weights and drop out, but in 2017, the RIS present a study about how a technique called cutout could improve regularization of convolutional neural networks. The idea behind this regularization technique is randomly mask out square regions of the input during training. We can achieve the same effect by randomly removing a few of the selected tiles. In the illustrations, we will be removing the gray tiles during training. So on top of selecting a few tiles, the tiles with more tissue, we will be randomly eliminating some of them to get the same effect of tile cutout. Well, and I think it was enough about preliminaries, and let's go through the solutions. The 11-play solutions, the 11-play solution by Yafos, and here is the summary for that one. For training, he used 128 tiles of size 128 from the intermediate resolution layer of the TIFF files. He applied out-of-all uncertainty denoising, and he removed about 1,400 Radboud and 300 Karolinska samples. He used a specific loss to minimize the Kappa matrix, so it was different to the one that I was using in the baseline. This one is specific for the challenge metric. As well, he was using the tile cutout regularization method, keeping 96 out of 128 tiles. Similar than in the baseline, he used ResNext 50 as backbone with a concat tile pooling head trained using for cross-validation. In addition, he used augmentations with augmentation, including geometric and color transformations. The models, the number of epochs range from 32 to 48, depending of the model. During inference, he used a majority voting assembling of 8 models, each one trained in a different train validation split, and a 6-fold test transformation augmentation. He obtained a public score of 91.7% and a private score of 92%. And this was one of his conclusions. The model is the minor thing in this competition, and the main role is played by considering the noise. There is no magic model, but there are hard work and solid understanding of the task and the data. Okay, that was the 11th place solution. There is any question? Okay, well, if there is not, I will go with the first place solution. And here's the summary of the winning solution by PANDA team. Instead of concatenating the tiles after the convolutional backbone, as suggested by Yafus, this team concatenates the tiles to form a large square image, which will be the input of the backbone. They train two similar models based on efficient, one using generalized mean pooling and other using average pooling before the fully connected layers. For training, they perform label denoising using the Fantaros architecture, the one in the left, and the one based and that this one is based on efficient P1. They use different tile resolutions and a special way to represent the output called sorted binning or binding. For this one, an ISUP grade of 3 will be represented by this vector of 3 ones, and similarly with an ISUP of 5. If we optimize the model using binary cross entropy, we obtain one way of ordinal regression. And it is an intermediate problem between classic regression and classification, but for ordinal labels. Using this model, they obtain a public score of 0.9 and a private of 0.94. And that was the winning solution. And one of the competitors in this team says that we could get good score because our model is strong against easy data but weak against difficult data. That was his conclusion. Well, that was the first place solution. I don't know if you have any question.
I just want to highlight something that I noticed between the two teams, and it's the way that they represent the labeled data. So you said the second team represents an ISUP score of 3 with 3 ones and then 2 zeros. And do you know how the previous team had represented that same label of 3? Did they just choose like a 1 number representation of it?
Well, for the baseline, for the this one was the same architecture that I was using for the baseline, and in that case, the output was categorical.
Mm-hmm.
After, well, you have to, well, in here you have six outputs, but you will be computing categorical cross entropy, and you have 6 outputs, and it is supposed that only one of those will be a 1. No, it is similar to a single class classification problem.
Right.
A multi-class problem.
So all of the classes are completely independent, and the class of 3 is just as independent from 4 as it is from 5. So the model, if it's wrong, it doesn't necessarily know how close it was to the right answer.
Yeah.
Whereas in the second one, they're not completely independent because they only differ by that one digit.
Yeah, and actually you can kind of debug your outputs because you have the same 5 outputs or 6 or 5 outputs after the fully convolutional block, but then you might see that maybe one of your outputs is scoring 1001 and it is not a 2, so you might conclude something about it, I would say. um, yeah, but that's a good point what you mentioned.
Yeah, that sounds like a cool approach that they took.
Yes. Well, I'm done with the solution, so I will enter in leaderboards check discussion. That was a completely different thing. And a recurrent discussion among the competitors was that the check between the public and private leaderboards was huge. In this leaderboard here, we can see a competitor who got into the money after overtaking almost 200 competitors. However, it was not just a shake in position, but also in scores. To understand the shake better, I decided to explore the leaderboard data. Getting the public rank was easy, but the private was a nightmare. But well, after I did it, first I plotted the private and public leaderboard scores histograms to see if any difference. And from here, it seems that predicting for the private dataset was somehow easier than the public one. Another experiment that I did was compare the position in the public and the private leaderboards on a scatter plot. The color of the plots is the difference in position. The yellow color represents a much better position in the private leaderboard, and the dark blue a worse one. There are several things to highlight here. And first, some lines in the scatter plot call my attention. It turns out that both the public and private scores were constant along these lines. And I thought I could recognize what are the public kernels that the competitors were using for those submissions. The one that is in magenta in the upper right corner is the YAFOS baseline model that I run. The one in orange was the Hackchen model using efficient net B0 and as his backbone. In fact, this was the starting point for Arutema's model in the first place solution, which uses 36 tiles of size 256. So it is a known model. And he was using the binning label and binary cross entropy loss. So exactly the same one that Arutema was using in the first place solution, but in the Arutema's model was somehow fine-tuned. The purple the purple line is the same as Hackchen method, but using efficient net B1, and that was what I could conclude. Here we can see that the guy in the third place is in that position in orange, and he's the one that won, the one who won the lottery. And he mentioned he used the Hackchen approach, but it was not. I was not able to follow the discussion on his solution. It was not pretty well documented, so I don't have much details. But it was pretty informative. So the scatter plot. I mean, I think that it is clear what participants were doing for submission, or at least for some of them. I don't know if you have any question of this part.
Yeah, how are you able to tell that everybody was using that one Hakishin? Is it just because they all got the same score?
They got the same score in the public and the private leaderboard. So, well, I know that's not. I cannot say that for sure, but they were the same scores up to the 10th digit in the decimal expression. So
how do you know what portion of the leaderboard was just using that like public kernel essentially as their solution? It looks like quite a few people.
Yes, and actually the competition for this competition part, the number of participants was 1,010. But I would say that at least in this line, there are almost up 300 in this one, in the orange one.
Mm-hmm.
So I would say more of the half of the participants used those models. I think that, well, I don't know. I couldn't check any kernel, but I would say that the ideas for approaching this problem were not very different. So,
Mm-hmm.
and most of them, or at least all of them that I saw, were using the tile method that IAFOS proposed. So I think that's the case. Well, I have some comments about why it could be the leaderboard shake, and many participants report higher trained cross-validation scores but got worse public ones. Similar to what happened with the public and private scores. Some possible reasons for this phenomenon are that there are significantly differences between the sets, the training and the two test sets, and the distribution of those sets, or maybe because of label noise, or also because of the fact that the quadratic kappa loss was not defined as a loss expectation, or the expectation of losses. Usually the loss function defined in such a way is well behaved for large enough sample sizes, and maybe in this case the evaluation set size were not large enough to estimate the out of sample loss. I think that's the more plausible reason, but I don't know. Well, I will finish with some conclusion, or at least some lessons that I got, and those are that the tiles method was indisputably the way to deal with this large data set, and the studied solutions rely on denoising method to boost the kappa score and prevent the shake. Participating in a large image recognition competition without your own GPU will be a headache. I really experimented, and I don't know. So it was interesting because I learned a lot of things, but it took me a while running some experiments, and I had that quota limit that I exceed quickly. So 30 hours a week is nothing when you are experimenting. I finished with a question, and it is is it worth participating in a competition with such a level of noise label? Because many participants abandon the competition for this reason. So that's a question that I have. I learn a lot, and it's worth participate, but I don't know. Some people think that's not the case. Well, that was everything. So, thank you.
I'm curious if people have thoughts on that question. I kind of feel like that's just the world that we live in. Like, we often face noisy data, and there's lots of techniques, as the winner showed, to try to tackle that part of the problem. So I think it's actually pretty valuable to work on a problem that has that noise.
And what do you think about, I think the experts in the expert side, even between, if you compute the scores between two different experts, it seems that one is not able to do it perfectly. So I think it is also about the labels. So maybe in the real life you can do something with the data, but in a competition you cannot. So maybe that's a point to study. Always is good to have like better techniques, but for the noising, I mean, or studying this kind of phenomena. But if you can clean your data, why don't?
Yeah, that's a good point. I guess it really depends on what the participant is trying to get out of the competition, right? If they're really interested in learning about developing their machine learning knowledge, then dealing with all this noise is not ideal. Whereas if they're trying to learn really about the whole data science process in general, then that maybe it is.
Yeah, I think that's a good point.
I certainly, at work on the project that I deal with, there's also a lot of noisy labels, and we've developed a lot of tools that essentially are aimed at cleaning up that noise. And so the amount of time I spend on developing machine learning algorithms is actually very little, and the amount I spend on all the other aspects of the problem and cleaning up the data and getting good labels for that machine learning is that takes up most of my time.
Makes sense. Yeah, there are some cases where you cannot do anything, and you have to just work with that.
Have you thought about buying a GPU, or thought about getting access to a GPU in some way? Because I mean, I totally am sympathizing with what you're saying. It's just so hard to do anything without at least that as a resource to be able to use, and especially as you're learning this stuff.
Yes, I have thought about it. Well, I need to get a job, and then after that I can spend on a bunch of GPUs if I have the money. Yeah, because some of them are expensive now.
All of them are expensive.
It's certainly an initial investment that is required, unfortunately, especially when you're dealing with images. I don't know if they're that expensive though. I mean, you could get a pretty good system for $2,000, I guess.
Yeah, at least for the problems I was working with before, I was using collab GPUs, and they were kind of enough. Yeah, but with this huge data set, it is kind of an issue just loading the data in my drive or so not. So that's not something simple to do. But also it was important for me, or at least a good point, learning fast a little bit, of PyTorch. I think that those two frameworks are not pretty different, but the syntax is kind of a little bit. So the concepts are the same, no? The theory is the same, but it was an interesting learning.
How did you like one compared to the other, PyTorch versus TensorFlow or Keras?
Well, I feel more comfortable in TensorFlow and Keras because yeah, I am a newbie here, but maybe I think that you have, as people say, you have more control on details using PyTorch.
Mm-hmm.
And what do you work with? So which one do you use?
I've been planning to make the switch over to PyTorch for a while. I just, as I mentioned, don't have much time to spend on ML these days. But yeah, I think I would like to move towards PyTorch based on everything I've heard from it. Well, we can say some of this for after the presentation. Does anybody else have any other questions for Juan about any part of the presentation?
Yes, I have one question, but it wasn't about this presentation. I want to take advice for a project. It was a statistical approach for that one. It is actually a Kaggle competition.
Oh, okay. Let's leave that until after because we'll have to end the recording at a certain point.
Yes.
So any other questions to Juan? Okay, I thought this was great, and Juan, it's a really really nice topic you dealt with, and as R posted in the chat, like this is a really big issue, really important issue, and trying to solve and try to do a better job at. So, can everybody join me in a round of applause for Juan in 5 seconds? If you just could unmute yourself. This is how I like to end these recordings, I guess. So 5, 4, 3, 2, 1.